Water as a solvent. Now, water is a very, very common solvent. It's used in a lot of applications, even inside you. Since you're 70% water, a lot of your body is, and a lot of your chemicals and proteins and whatever are dissolved in water. That's what you're made out of, 70% water. And so water is a very common solvent for many different things. Now, what makes water special? For one thing, water is very polar. It's very polar. Which means since it's polar, it's going to dissolve polar compounds as solutes. And not only that, but it's going to dissolve soluble ionic compounds. Now, why is water very polar? Now let's go back to the geometry. Let's go back to our Lewis diagrams. And if you recall, water looks like this. We have the two hydrogens, H2, with the oxygen, with the lone pairs sticking out. And if you recall, the electronic geometry of water was tetrahedral, but because of these lone pairs, the molecular geometry is bent. Now, because it is a bent molecule, it allows the dipoles that are being formed between the oxygens and the hydrogens to go in a direction. Now, oxygen is very electronegative. Oxygen is very electronegative. Oxygen is very electronegative compared to the hydrogen. And if you recall, to have a polar bond, you have to have differences of electronegativity. Now, the oxygen is very close to fluorine. Fluorine is the most electronegative element. The closer you are to fluorine on the periodic table, the more electronegative you are. The further away you are from fluorine, the less electronegative that you are. Now, oxygen is very close to fluorine if you look at your periodic table. And also, if you look at hydrogen on your periodic table, you will see that hydrogen is all the way to the far upper left. It is far away from fluorine and oxygen as you can get. And so there's a very large difference in electronegativity between the oxygen and the hydrogen. Now, being electronegative means that the oxygen wants the electrons more than the hydrogen. And so it's going to have a tendency to draw the electrons towards the oxygen and draw them towards the oxygen. And when they do that, they're going to add up so that it's going through the oxygen that way. So the electrons are being drawn to the oxygen with a net going above, beyond the oxygen. Now, we have to remember that electrons are negatively charged. They have a negative charge. So if you get more electron, not complete electrons, but you get more electrons spending more time towards the oxygen, well, this end over here is going to have a partial, what's known as a partial negative charge on the oxygen end. Now, this is not a complete charge. This is not like Na+, sodium plus, which has a complete plus charge, or oxygen 2-, O2-, which has a complete 2 negative charge. This is a partial negative charge because it's not really moving the electron completely to one side. It's just spending more time over on the oxygen. Now, conversely, if you're moving electrons away from the hydrogens, then you have less electron density on the hydrogens, and so you have less negative, which would make it more positive. And so on the hydrogen ends, these become partially positive. So the hydrogen ends are partially positive on the water molecule. Now, this is a permanent dipole in a sense that as long as this molecule is together, the oxygen is going to be pulling electrons this way, and the hydrogens are going to be electron deficient, and they're going to end up having plus net charges on that end of the molecule. So the head of the water molecule is partially negative, and the tail of the water molecule is partially positive. Now, since this is very electronegative and this is making a very strong polar bond here, so this is particularly a strong force. And it turns out that for oxygen and nitrogen and fluorine, if they're paired with a hydrogen, then we call these H bonders or H bonds. They make hydrogen bonds. So you got NH, OH, FH. So if you see a nitrogen paired with a hydrogen, you know it's going to make a hydrogen bond. If you see an oxygen with a hydrogen or a fluorine with a hydrogen, you know it's going to make hydrogen bonding. Now remember, this has a permanent dipole. Hydrogen bonding is a special case of dipole-dipole. It's still dipole-dipole, it's just very strong. Other things can have dipole-dipole polarity, but not be quite as strong as water or any compound that has NH, OH, or FH in it. So how does water form a solution? How does water act as a solvent? Now, if we look at water molecules, you recall that one end is a partial negative and the other end is partial plus. Now, opposites attract. Opposite charges attract. Pluses and minuses attract. So if this water molecule sees another, let's say, an NH, which makes hydrogen bonding, well, this hydrogen is going to be attracted to the negative end on that ammonia. They'll be attracted. And so if you surround this guy with waters, the heads are going to be attracted to the hydrogens, because these are partial pluses on the hydrogen. And what's on the oxygen? We just looked at it, and it's partial negative on that end. So we get these attractions in between the water molecules and that NH3 ammonia. And so this force right here is enough to separate out the ammonia from other ammonias and keep them separated, and that's what it means to be dissolved. And so the water surrounds the polar molecule, Now, what happens if we have some sort of like ionic compound? If we have an ionic compound like sodium chloride, what's going to happen is something very similar. Here's my sodium ion, and let's say we have our chloride ion down here. What's going to happen to these water molecules as it sees that positive charge and that negative charge on the sodium and the chlorine? Well, what's going to happen is that the head, which is on the oxygen, on the water, is going to be attracted to the sodium, like such. And they will actually form a cage of water molecules around this sodium ion. Now the same thing's going on over here, except the tails of the water molecule, which is the hydrogen ends, which are partial positive, they're going to be attracted to the chloride. And so the tails, the hydrogens on these waters, is attracted to the chloride, making once again, like we did over here with the NH3, making once again a cage, a three-dimensional cage around that chloride. And the same thing over here with the sodium, it's making a cage, a three-dimensional cage surrounding the sodium plus and the chlorine minus. And so the net effect of all of this is that you have enough charges on these hydrogens, enough charges on these oxygens, that the chlorine and the sodium really can't see each other anymore. Now, they will occasionally, if they get close enough, they will recombine momentarily, but then the water molecules will just tear it right back apart. So that's how an ionic compound gets dissolved in water, and this is how a polar compound ends up getting dissolved in water. And it's all about these hydrogen bonds, and it's about these dipole-dipole interactions. This is dipole ion, and it's also a strong force. And so the water molecule just surrounds, the water molecules just surround whatever it is that has dissolved in the water.